Hi everyone! In this video we are going to cover acetoacetic ester synthesis, which is really similar to the malonic ester synthesis. So in this reaction, again we're going to convert halide into something different, but instead of a carboxylic acid, this is going to form a methyl ketone. So we're replacing that halogen X with this set of atoms. Oh, methyl ketone. Also notice that we're adding 3 new carbons here. So the acetoacetic ester synthesis converts a halide with to, let's see, a methyl ketone with 3 new carbon atoms. Now, in the malonic ester synthesis, we use diethyl malonate. In this synthesis, we're going to use something called ethyl acetoacetate, which is really similar, but instead of 2 esters, there's 1 ester and then 1 ketone. Okay, so let's look at the mechanism, and again it will be really similar to the malonic ester synthesis. So we're going to start with that ethyl acetoacetate. And again, that alpha carbon in the middle has really acidic protons because the enolate is extra stable. So we're going to use our alkoxide base again, and it has to match the leaving group of the ester. We're going to leave electrons behind on the alpha carbon, which will give us our enolate. All right, so far looking really similar to malonic ester synthesis. So next we're going to add our alkyl halide, which again should be a simple alkyl halide. And the enolate will act as a nucleophile and attack the alkyl group, which will leave electrons behind on the halogen. All right, so now we've got that alkyl group on the alpha carbon. Now the next step, we're going to use acid, and in the malonic ester synthesis, we were able to convert both esters into carboxylic acids. But notice here we only have 1 ester. So if we add acid, we're only going to convert the ester into a carboxylic acid. The other side, the ketone, just stays the same because it doesn't have a leaving group. All right, now I'm just going to rotate that carboxylic acid like I did last time. So I'm going to rotate it so that the carbonyl group is pointing down and then the alcohol is pointing up so that we can show the next step. Now notice that the other carbonyl group is now really close to that hydrogen. So the pi electrons from the ketone group can grab onto that proton. The electrons between oxygen and hydrogen will be left behind, And then that's going to break our bond down below. So similar to last time, with our malonic ester synthesis, we're losing CO2. So that is our leaving group. Okay, so then we end up forming, oh, actually, let me flip these. So we're forming CO2 gas, which will just kind of bubble away or float away. And we're also going to form an alcohol with a double bond. So that makes it an enol, right? And the enol will tautomerize into a ketone. And remember, ketones are more favored over enols. All right, so again, we're just replacing that halogen in our alkyl halide with this methyl ketone. So let's do a challenge problem now that we've seen both malonic ester synthesis and acetoacetic ester synthesis. Okay, so what if we have the following? And then we treat this with alkoxide base, so the ethoxide base, followed by CH3I, so that is our alkyl halide. And then finally, we're going to add acid and heat. What do you think the product will be? And I'll give you a hint. The product has a ring system. So see if you can figure out the product for this challenge problem. You can pause the video, and then when you're done, we'll go over it together. All right, so looking at our series of steps here, in the first step, we're adding that alkoxide base. So that's going to deprotonate one of the alpha carbon carbons that we have. So this molecule is pretty symmetrical, so it doesn't really matter which alpha carbon we deprotonate. So I'll just deprotonate the one on the right here. All right, so that's going to form our enolate. All right, and then the negatively charged carbon there can attack the other carbonyl group, and we'll move electrons up to oxygen. So it looks like we're going to form a ring in this step. So let's figure out how many carbons are in the ring. So we've got 1, 2, 3, 4, 5. Okay. So let's draw a 5-membered ring, and let's number our carbons. Let's see. So we've got 1, 2, 3, 4, 5. Okay. So on carbon 1, we have this group, the ester group. So we'll draw that in there. And then on carbon 5, we have a negatively charged oxygen, as well as our ethoxy group. Okay, now the ethoxy group would be a really good leaving group, right? So in the next step, we can reform our double bond with carbon and oxygen. and our leaving group will head out. Okay, so at this point, remember that we do have that alkoxide base still hanging around. It just left the molecule, and we have an alpha proton that it can take. So we're going to form another enolate. Okay. So in the next step, that's where we're going to add that alkyl halide. And I'm actually going to do this on the next slide because I'm running out of room here. Oh, whoops. Let's see. Actually, I'll try to just squeeze it on here. Okay, so let's add that CH3I group. So our enolate is going to attack the methyl group, which will leave electrons behind on the halogen there. Okay, so now we're going to see the addition of a CH3 group on that alpha carbon. And then now we're going to add acid. And the acid is going to convert our ester group into a carboxylic acid. All right. And now if we also add heat, we'll see our ketone grabbing onto that hydrogen from the carboxylic acid. We'll leave electrons behind, and then we're also going to, break our bond down below. Let's see, I'm having trouble squeezing this in here. So we're going to lose that CO2 group. And I'm just going to skip a couple steps here just because I'm running out of room. But remember from our previous synthesis or mechanism, we saw that we'll form an alcohol with an alkene, so an enol, and then that's going to tautomerize into a ketone. All right, so then we would end up with our final product, which has a CH3 group on the alpha carbon, and then we have our ketone left behind. All right. So I kind of ran out of room. This was a long reaction, but mainly I wanted to show you here that you can also have intramolecular reactions with the malonic ester synthesis and the acetoacetic ester synthesis. So keep that in mind that sometimes you might see a ring formation in your reactions. And you might also see this on sapling too. Okay, in the next video, we're going to start discussing conjugate addition reactions. So these reactions are called Michael reaction, and then we'll kind of wrap up with the Stork enamine synthesis and Robinson annulation reaction. So we're starting to get to the end of our chapter here. So I will see you then.